All right, let's dive into the world of acids, bases, and salts. Now, I know you might be thinking, chemistry class, but stick with me because this stuff is everywhere. It's the secret science behind the taste of your food, the feel of your soap, and honestly, so much more.
I mean, have you ever really stopped to think about it? Why is a lemon so incredibly sour? That sharp tang is literally an acid at work. And that slick, almost greasy feeling of soak? Yep, that's a base. We are surrounded by these things every single day.
So here's what we've got on tap. First, we're going to get to know acids and bases, our key players. Then we'll see what happens when they get out into the world and start reacting. After that, we'll uncover the secret to what makes them tick. And finally, we'll wrap up with the pH scale and why all of this really matters to you.
Okay, first things first, let's properly meet our two main chemical characters. What exactly makes an acid and a base a base?
Well, there are some pretty clear giveaways. For acids, think sour, like in lemons or vinegar. Bases, on the other hand, tend to be bitter. But since we can't taste everything, the real classic test is with litmus paper. Acids turn blue litmus red. Bases do the exact opposite. They turn red litmus blue. It's a simple, visual clue that never lies. Right, and this is a really important question, because seriously, do not go around taste testing mystery chemicals. So how do we figure it out safely? Well, the answer lies in a special class of substances called indicators. An indicator is pretty much exactly what it sounds like. It indicates if we're dealing with an acid or a base just by changing its color. Litmus is a perfect example, and it's totally natural. It comes from lichen. You might even have another natural one right in your spice cabinet, turmeric. And this is such a perfect real-world example. You've probably seen this happen. You get a bright yellow curry stain on your shirt, you go to scrub it with soap, which we know is a base, and for a second, the stain flashes this deep reddish-brown color. That's it. That's the turmeric and the curry acting as a natural indicator. How cool is that?
So we know how to spot them. But what do acids and bases actually do? Well, their true personalities really come out when they start reacting with other things.
Okay, picture this classic lab scene. You take a piece of metal, say zinc, and drop it into some acid. Immediately, it starts to fizz like crazy. Those bubbles are a gas. And here's the fun part. If you catch that gas and bring a lit match or candle to it, you get this really satisfying pop. That pop is the telltale signature of hydrogen gas. So what's actually happening there? It boils down to a really simple rule. When an acid reacts with most metals, you get two things, a salt and that hydrogen gas we just heard go pop. And it's not just metals. Acids also have a really dramatic reaction with things called metal carbonates. Think of stuff like chalk, limestone, or even marble. Add acid to those and you'll get a salt, some water, and a whole lot of carbon dioxide gas. That's all the fizzing and bubbling you see. But maybe the most important reaction of all is what happens when an acid and a base finally meet each other. This quote really nails it. They are chemical opposites, and their superpower is that they can completely cancel each other out. This is exactly why people might drink a solution of baking soda, a base, to help with indigestion from too much stomach acid. And here is the simple, beautiful formula for that interaction. It's called a neutralization reaction. A base plus an acid gives you a salt and plain old water. Two totally neutral things. It's the ultimate chemical showdown. And in the end, everybody's chill.
Okay, so we've seen what acids and bases do, but now for the big question, why? What is the one secret ingredient that all acids have in common, and what gives all bases their power? Let's pull back the curtain.
And here it is. This is the secret right here. It all comes down to tiny charged particles called ions. When you put an acid in water, it releases hydrogen ions, H+. That's the source of all its acidness. And bases, when they're in water, they release hydroxide ions, OH-. These little ions are the key to everything. But, and this is a huge but, there's a catch. They can only do this, they can only show their true colors when they're dissolved in water. For instance, if you have dry acid powder and you touch it with a piece of dry litmus paper, nothing happens. Nothing. It's only when water is in the picture that those H+ ions can break free and do their thing. And that leads us to a key chemistry term, an aqueous solution.
It sounds fancy, but all it means is that something is dissolved in water. For acids and bases, water is the stage. It's the environment that lets them release their ions and unleash their chemical powers. So we now know that H+ ions are what make an acid. But clearly, some acids are way stronger than others. Lemon juice is one thing, but battery acid is something else entirely. So how do we measure that strength? Well, that brings us to the famous pH scale. The pH scale is just a brilliant tool that gives us a simple number from 0 to 14 to tell us how acidic or basic something is. That little p, by the way, comes from the German word potens, which means power. So pH literally means the power of hydrogen. The more hydrogen ions, the lower the pH number and the stronger the acid. And reading the scale is super simple. Anything with a pH below 7 is acidic. Anything above 7 is basic, which is also called alkaline. And right there in the middle, at a perfect 7, is pure, neutral water. So you can see where things like lemon juice and a baking soda solution fall on the spectrum. So why does any of this matter to you? Oh, it matters a lot. This isn't just a lab concept. It's critical to life itself. Our bodies have to stay in a super narrow pH range to even function. Acid rain, which is just rain with a low pH, can totally wreck aquatic ecosystems. Our own stomachs use powerful acid to digest food. Even the plants that grow our food need the soil pH to be just right. It's literally everywhere. So we've gotten all the way from the simple sour taste of a lemon to the health of our entire planet, and it all traces back to these basic chemical ideas. It really makes you think, doesn't it? If acids and bases are this fundamental, what other mysteries in our everyday world could be explained by their invisible dance?
All right, let's dive into the